Hello everyone, welcome back to the numerical methods course. From this section we are going to learn about curve fitting, and that's why in this lesson we are going to learn about least square regression. First of all, let's see what is the purpose of curve fitting. Suppose you are given some of the data points practically in an experiment, and you need to know the values of those parameters within some range at different points that is not given, and that's why you need to have a function that can approximate a value at that unknown point. So curve fitting is a good choice for that purpose. Besides, sometimes it might happen that you are given a very complicated function and you need to know the values at different points, but the working procedure with that complicated function is very much time consuming and very much hard. And in that case, what you can do, you can plot various points and function values, and you can fit a new simpler version of that function to work with your problem. So for these reasons we need to fit a curve within the data points. So there are basically two types of curve fitting. One is regression and another is interpolation. There are some basic differences between these two approaches, and in the next lessons and within this lesson we are going to see some of the methods that are used within these two categories. Let's first look at the regression type of curve fitting. So for the simplest example of regression is linear regression, and it is also known as the least square approximation. The reason behind this name is it will be very much clear at the end of this lesson why it is named as the least square approximation. So let's work through the algorithm. In linear regression, we fit a straight line or a linear line through the data points in the space. So, for example, if you were given some of the data points, something like this in the figure, along the x-axis and in the y-axis, we are given some data points and plotted some of the points in the figure, and you need to have a curve or a straight line that best approximates the nature of these data points. For example, if we fit a straight line, look at this in the figure, the straight line actually conserves the nature of the data points. As a result, look at this, as long as the x-axis increases, the value of the x increases, the value of the y also increases. So this is something like a linear nature between the x and y variable. So we can fit a linear curve or a straight line within these 2 points and within these 2 variables. The equation of this fitted straight line is something like this: y equal to a naught plus a1x plus e. Here a naught and a1 are coefficients which represent actually the intercept of the line in the y-axis and the slope respectively, and e is known as the error or residual between the model and the observations. So what is this term, this error term? Look at this in the figure. At point x equal to 5, the true value is denoted by this black dot, and the approximated value of this point at x equal to 5 is approximated by the straight line at this point. As a result, there is a slight difference between these two results, the true value and the approximated value, and the difference is known as the error at this x equal to 5. But this straight line is fitted in the whole space. As a result, there is some error at each of the data points. So how can we actually define a single term, a single error from all of these errors? And that's the main concern of linear regression. So we have to find a definite definition to denote this error term as a single term within this equation. So if we modify the equation in some way, we can get an equation of the error in terms of other parameters. Look at this here, error is equal to y minus a naught minus a1x. Here y is the true value of the data point, and the approximated value is denoted by these two terms, a naught and a1x. This is the equation of a straight line, fitted straight line. So y is the true value and the other two terms denote the approximated value. So the difference is known as the error. So we have to actually we have to minimize this error term, because the main purpose of fitting a curve is that the error term is decreased as much as possible. So we have to minimize this error term, and that's the main target of any kind of regression. So there are many criteria through which we can actually minimize this error. So we have to find out the best fit criteria, which criteria actually best fits our main purpose. So first of all, in criteria 1, let's see what we can do about all of the error terms. So at each point there is an error between the fitted curve and the main data points. So these errors are denoted by y minus a naught minus a1 xi. So at each of the points xi there is a true value yi, and the difference between these two quantities is the error. So at each point we can get an error term. So if we sum over all of these error terms from I equal to 1 to n, there are n space n points in the x-axis, so we can sum all the error terms. So this is the summation of all the errors. So if we can somehow minimize this summation of errors, so that would be a good practice actually to minimize the error terms. So we sum over all of the error terms at each of the points, and then we try to minimize this error. So this is in criteria 1, where we can actually sum over the errors. So there is some slight loophole within this definition. This is an inadequate criterion. Why? Look at this figure. In this figure, there are 3 data points. The 3 data points are denoted by these 3 black dots, okay, and the middle point is denoted here. So if we fit a curve through the data points, something like this, a line that goes through all of the data points, this black line, a solid line. So also we can fit another line which is the dashed line, which goes through the midpoint, but it doesn't go through all of the 3 points. So that's the difference between the two fitted curves. But actually in both cases the error is 0. In the first case, the solid line goes through all of the 3 data points. As a result, the error is 0. Why? Because the approximated values and the true values are same. So the differences are 0. But in the second case, for the first data point here, for this point, the error is positive. But in the second, for the third point, the error is negative. So these two terms, the positive error and the negative error, cancels each other, and also there is no error related to this middle point, because the dashed line also goes through this point. As a result, for both of these fitted curves, the error term is 0. But actually the most desired curve is the solid line. But if we fit the dashed line, this would also give us a 0 error. But that is not acceptable. As a result, this criterion, which is the summation over the error terms, is not actually adequate. So this criteria does not fit our purpose. As a result, this criteria is not adequate. Another approach, the second criterion, can be to minimize the summation of absolute errors. So we take all of the individual error terms, and we take the absolute values and then sum over all of the error terms. As a result, we would get a single error, summed error in this definition. But this criteria is not also adequate. Why? Look at this figure. In this figure, we have 4 data points, 4 black dots. These are the data points. So we need to fit a curve within these data points. So what we can do, we can fit a curve. So let's say we have 2 dashed lines already fitted in these 4 data point space, and we can actually fit any curve that goes through within these two dashed lines. Okay, that goes through within these two dashed lines. As a result, in all of those cases, the dashed lines in the figure will minimize the sum of the error of the absolute values. So look at this, we can fit a line like this, something like this, and then this green curve which goes through these two dashed lines also, and all of those cases, in all of these cases, the summation of absolute errors will also minimize in the same way, but none of these actually denotes the best fit, as in there is no unique fit actually. We can fit a lot of curves within these data points and not a best curve. As a result, this criterion is also not adequate. The third criterion is we can minimize the sum of the squares of the residuals or the error terms. So for example, we have the measured yi values, and we get the model values. So that means these are the approximated values yi model, and these are the true values yi measured. So we take the differences between those and square each of the error term, and then sum over all of the error terms. So this is actually the sum of square of the errors. So these criterion actually meets most of the purposes of the best fit criterion. This criterion has several advantages, including the fact that it is a unique line of given set of data within the minimized error. That means we will get a unique line, the best line that goes through some of the data points. So among these three criterion, this third criterion, which is the summation over the square of the error terms, is the best one. So that's why it is named as the least square regression. We take the squares of the errors and then we measure the least value of that error term. So that's why it is known as the least square regression, and that's the reason it is named as least square regression. So we need to minimize this error term, this summation of the square of the errors. So we denote this term as a new notation SR. It denotes the summation of the square of the error terms. So this is also known as summation over I equal to 1 to n. That means sum over all the data points and the error terms. Inside the summation, we take the error terms square. That means yi is the true value, and a0 plus a1x, this is the approximated value from our fitted curve. So we take the difference between these two terms and then take the square. So that makes the square of the error term, and then we sum over all of the data points. So that's the definition of the squared error. So what we want to do, we want to minimize this error term. Okay, that's the purpose. We want to minimize this error term. That means we want to fit a curve that has a least error within these data points. So how can we actually minimize this? To minimize this, we also, to get the best fit curve, we need to find these two values, a0 and a1. These are the two parameters of the fitted curve, fitted straight line. So we need to find out these two values, a0 and a1. a0 is the intersection in the y-axis of the straight line, and a1 is the slope of the fitted straight line. To determine these two values, a0 and a1, we want to differentiate this term, SR term. So if we want to differentiate, if we differentiate this summation over error square term with respect to a0, we will get a parameter something like this. So if we differentiate this term, so this 2 is going to come over here, and 2 times summation over all of this term, and then we also want to differentiate the inner term. That means it would give us minus term here. So that is the differentiation with respect to a0. But if we want to differentiate with respect to a1, we will get something like this, minus 2, and because there is this term minus a1 times xi, that's why we get this term xi. So these are the two differentiation terms with respect to a0 and a1, and since we want to minimize these two error terms, so whatever this independent parameter is, that means this error term should be minimized. Okay, so that's what we are going to do. So we want to equal these two terms equal to 0, because the differentiation with respect to a0 and a1 should minimize the error term. As a result, that differentiation value should be equal to 0. Okay, so we equal those two equations equal to 0, and if we simplify those two equations, we will get something like this: summation over yi minus summation over a0 minus summation over a1 xi. So we just what we're doing, we are just taking the summation over individual terms in those equations. So we get these two equations. So within these equations there are two parameters that are going to be determined, a0 and a1. So we have two equations and two unknown terms, a0 and a1, and all other terms, xi, summation over xi squared, these terms are actually given. So these are the data points actually. So we need to solve these two equations and find out the values of a1, a0 and a1. So this is very easy actually. Look at this term, summation over a0. First of all, look at this term, summation over yi. Since we are given the data points, we can sum over all of the y variables and get this result. Then the next term, summation over a0. Since a0 is a constant term, so a0 will come out of the summation term. That means we can actually take this as a common part. So a0, and then summation over all the data points xi, which is there are actually n terms, n data points. So that makes this summation as n a0. So summation over a0 equal to n a0. Similarly, this a1 term, this third term, a1 is a constant, so we can take this as a common part and take this out of this summation 1 and say a1 summation over xi, that is denoted here. Similarly, in the second equation, the first term is summation over xi yi. So we are given all the data points, so we multiply each of individual pairs and then sum over all the data points. Similarly, in the second term, we have this a0 constant, so we take this part out of this summation and say a0 summation over xi. And then in the third part, a1 is also constant, so we take this out of the summation. That means it makes this a1 summation over xi square. Okay, so we are just simplifying these two equations into these two equations. So we need to solve these simplified two portions. So if we just solve these two equations through elimination or substitution procedure, we can just find that a1 is this term. It is just simple algebraic manipulation. So we can find the a1 in this way, and then a0 is also can be found from these two equations, which is y bar minus a1 times x bar. Y bar is the y bar is actually the mean or the average of the y values, and x bar is the mean or the average of the x values. So these are actually the mean values of the x and y points that we are given. So once we can know this a0 and a1 term from these two equations, we can actually know the fitted curve, because a0 is the intersection point of the y-axis and the fitted curve, and a1 is also denoted as the slope of the fitted curve. So a0 and a1 are the main two parameters that we had to determine from the best fit curve. So once we know a0 and a1, that's the result. That's actually the two parameters that are needed for defining the best fit curve. Also, we can determine other parameters like the standard deviation of the regression line. That means once we know the regression line, the fitted line, we can determine how that line actually deviates from the true values, and that is denoted by this formula SYX. This is the standard deviation of the fitted line or the regression line. So over this, SR is the summation over all of the error square terms and divided by n minus 2. N is the number of data points. So this is known as the standard error of the estimate. That means the more this value is, that means SYX should be minimized, because we want to minimize this SR term. So SYX should be minimized. So if we fit two curves, for the first one we get SYX1, for the second curve we get the SYX2, whichever is lower, that's the best fit curve. So we need to minimize this term also. Since we are minimizing this SR term, so this SYX, the standard error term, is also automatically minimized. Okay. Now let's look at these two figures. In the first figure, in both of these figures we are given the same data points. Okay, in the first figure we fit a line that is the average of all the data points. This is the average line or the mean line. But in the second case, in figure B, we fitted the curve, fitted the data points with a regression line. Okay, that's the difference between these two curves. This is the mean line and this is the regression line, the least square line. In the first case, look at this, the deviation of the data points from the mean line is much broader than those of the regression line. In the first case, the deviation is much larger than the second case. Since this is the best fit curve, look at this, the regression line actually captures most of the features of the data points, and that's why it gives us a narrow curve, a narrow peak over here. So that means the standard deviation is much lower in the regression line than that of the mean line. Okay, so let's look at an example here. We are given some of the data points. So we are given, let's say, 7 data points, 1 2 3 4 5 6 7, and correspondingly we are given the y values or the function values at these points. So for 1 we get the function point 0.5, for 2 we get the function point 2.5, and so on. Okay, so we need to fit a line, a straight line, a least square regression line, whatever you say, from these data points. So if you remember the two equations, A0 and A1, we can get all the terms from this table actually. So to get the values of A0 and A1, we need to determine certain quantities. For example, first of all, the value of n, the data points, is 7. Here we are given 7 data points, that's why n equal to 7. Next, we need to determine this summation over the individual multiplications, that means individual pairs. So for all of these data points, we sum over the xi times yi. For example, in the first case, for data point 1, we multiply 1 and 0.5, we get 0.5. Similarly, for data point 2, we multiply 2 times 2.5, so that's 5. So similarly, we multiply all of these pairs and then we take the summation, which is 119.5. Next, we need to determine the summation of xi square. That means we are given all the xi terms, we take the square of each of these xi and then take the summation. That means 1 square plus 2 square plus 3 square plus 4 square up to 7 square. We take the summation and then we get the value 140. Then we take the summation over xi, which means to take the sum over all of these determinants. That means 1 plus 2 plus 3 plus 4 plus up to 7. So we take the summation and we get the value 28. And then we take for A0 purpose, if you remember from the equations, from the equations of A0 and A1, for A0 we need to determine x bar and y bar. So how can we determine the x bar, which is the mean of the x variables? That means we need to divide the summation of xi divided by number of data points, which is 28 divided by 7. So that makes this term as 4. Then we need to determine y bar, but for the purpose of determining y bar, we need to determine summation of yi. So y bar can be determined as summation of yi divided by n, which is 24 divided by 7, which is 3.428571. So how can we take calculate this term, summation over yi? We take the summation over all of these y terms, which make this term as 24. Okay. So once we determine all of these terms, we can actually calculate A0 and A1. So the formula for A0 and A1 is already determined in the previous slides. So we just put in all of these values into the equations, into the formulas, and we can get the values of A0 and A1. So here a naught is 0.07142857 and for a1 0.8392857. So these are the two parameters for the least square line, the best fit line. Okay, a naught is the intersection point between the fitted curve and the y-axis, and a1 is the slope of the line. So look at this. This is the regression line that is fitted through the data points. So a naught, that makes the intersection with the y-axis, that this point, something like this, and a1 is the slope of this data, the slope of this regression line. Okay, so we can determine the error term, individual error terms for this straight line. From this straight line equation, a naught plus a1 xi, this is the straight line equation, a naught plus a1 xi. From this straight line equation, we can determine all the approximated values for all of these data points xi, and then we take the subtraction from the individual true points. So yi is the true point that is given in the table, and a naught plus a1 xi, this is the approximated value from the regression line. We take the difference and take the square, then we can get all the individual error terms for all of these xi terms. Okay, for x1 we get this error square term, for x2 we get this error square term, for x3 we get this error square term. Similarly, we get all the error square terms, and then if we sum over all of these errors, the error is 2.9911. so this is the least error, the summed over all of the error square terms. So this is the least square error. Okay, 2.9911. This is the least square error. That means the SR term. This is the SR term. And this is our main fitted line. This is a naught and this is a1. So y equal to a naught plus a1x. This is our least square regression line. And this is the least square error. Let's see how can utilize this least square regression into the other forms of data points. For example, if we are given something like this, this is the equation y equal to alpha 1 e to the power beta 1x. This is the curve of this function. Okay, we can linearize these function to actually feed a straight line through these data points. For example, if we take ln, natural logarithm, on both of these sides, we can get an equation something like this: ln y equal to ln 1 plus b1x beta 1x. So this is a modified equation from this one. We have just taken the natural logarithm on both of these sides. Okay, once we do this, we see the intersection of the y-axis is the ln alpha 1 and the slope of the curve is beta 1. So in this case, the independent variable remains x, but the dependent variable becomes ln y. So ln y equal to ln a1. This is the intersection of the y-axis of the data point of the fitted line, and x is the independent variable and beta 1 is the slope. So this is a modified version of this equation. Okay, so this equation is actually a straight line. So the independent variable is x and the dependent variable is ln y. So this is a straight line. So we are actually linearizing these function into a straight line so that we can fit a straight line least square regression line. Okay, similarly, look at this second figure. This is y equal to alpha t x to the power beta 2. So we can just modify this term into this linearized version. That means we take the log of both of these sides. That makes the equation something like this: log y equal to log a2 plus beta 2 times log x. So if we just plot this function with x-axis as the log x and y-axis as the log y, that makes the line as a straight line. So the slope of this line is beta 2 and the intersection of the y-axis is log a2. Okay, so that makes the linearized version of this function. Similarly, we can linearize this equation y equal to alpha 3x by beta 3 plus x. How we can linearize this equation? We just take the inverse of both of these sides. That means 1 by y, that makes the equation something like this. 1 by y equal to 1 by a3 plus beta 3 by a3 and in times 1 by x. So that makes the independent variable. 1 by x becomes the independent variable and the dependent variable becomes the 1 by y. So if we plot this function as 1 by x as the independent variable and 1 by y as the dependent variable, we will get a straight line. Okay, the slope of the straight line becomes beta 3 by a3 and the intersection of the y-axis becomes 1 by a3. So that makes the linearized version of these non-linear function. So what is the main reason that we are just linearizing these equations? We are just making a second version of these functions. That's because so that we can get we can fit a linearized equation, that means the least square regression line through the data points. Okay, so that makes the end of the least square regression analysis. So I have attached a MATLAB code of least square regression line within this set section. So please go through the MATLAB code, and in the next lesson we will learn about polynomial regression and multiple linear regression. So till then, thank you so much.